Hi, I'm Teacher In. In last chapter, we learned that head loss is mechanical energy loss of unit weight of fluid, and it shows as total head decrease in energy equation. We didn't talk about how it is generated and how to calculate it. In this chapter, we are going to solve these problems. We know that the fluid particles have relative motions in flow, so internal frictions happen everywhere. This kind of friction is actually shear stress in flow field. Hence, shear stress in flow lead to conversion of mechanical energy into thermal energy. This part of energy loss finally exhibits total head decrease, saying head loss. However, we noted that the relative motions of fluid have two types of performance. One is in layers, as we call the laminar flow. It looks smooth and regular, such as the tap water on the right and like the laminar diagram in the picture. The other type is characterized by irregular movement of the particles. It looks faster, more chaotic and diffusive, such as the tap water on the left and like the turbulent diagram in the picture. We call it turbulent flow. All natural flow are turbulent flows. Laminar flow and turbulent flow are two regions of fluid flow. Why we mention the flow type here? What's the relation between the flow region and head loss? It is because we found that different flow region has different resistance rule. We have to use different approach to determine their frictional factors. So, when we calculate frictional head loss, we must make clear the flow region at first. Another important thing that we need to understand is that there are two kinds of head loss. One is generated in uniform flow or gradually varied flow, which is proportional to the travel length. For example, the head loss in straight pipe flow, where the streamlines are straight and parallel, like in the picture. This kind of head loss is called major head loss or frictional head loss. The other is generated in a local place where the boundary is intensively changed, like valve section in upper picture and the connection region between the pipes of different diameter in lower picture. You can see in this kind of places, the streamlines cannot stick to the boundary for a distance due to inertia. We can see there are a lot of vortex in the pipe corner. These vortex have high-speed rotations and generate high shear stress that will cost much energy and decrease the total head a lot. Therefore, in short distance or in local space, there's a big head loss happened. It is called minor head loss or local head loss. It depends on the shape of the boundary, and there's no regular rule for its resistance coefficient, although the origin of it is still friction. In the following learning, our emphasis will be put on frictional head loss or major head loss. This is a summary. Let's take a look at two kinds of head loss along a pipe flow in the picture. At the entrance of the pipe, as the boundary changes abruptly, there's a local head loss denoted by HL entrance in the picture. So the total headline, or EGL, steps down. Then the flow goes into the straight part of the pipe and has frictional head loss only. EGL becomes a slope line. When the flow comes to the valve that is half open, local head loss appears. Here, the actual EGL is the dashed line at valve section, but we take it as a step down for simplicity. The step down or the local head loss is HL valve in the picture. After the valve, the flow becomes uniform again, so EGL turns to a slope line correspondingly. Then, at outlet of the pipe, the streamlines will diverge strongly, so another local head loss HL outlet comes out. We also see on both tank sections EGL are horizontal because the velocity in the tanks are so small that we can treat it as zero. No motion, no head losses. Here there's still another line, HGL, hydraulic grid line. It's only a velocity head lower than EGL. Please answer me why in water tank two lines are coincident. In general, major head loss is denoted by HF, while minor head loss by HJ in our course. For a flow ridge, total head loss is the sum of all major head losses and minor head losses on the ridge. Look at picture. Pay attention to the total head loss of pipe ridge AD, which is denoted by HWAD and shown by a red double arrow line. It is the vertical height from beginning to end of the total head line. The two ends of the total head line are shown by two small red dots in the picture. The line that is parallel to the total head line is piezometric head line. I use HP to indicate it. Two ends of it are shown by green dots in the picture. Here are some questions for you. Why in the upstream, red dot and green dot are on the same level? Why in downstream, red dot and green dot are separated, and the green dot is on the pipe center? Now, how to calculate head loss? We have Darcy's resistance formula. It can be derived by dimensional analysis. We are not going to talk about that here. What we need to do is to use it. First, for the two expressions in the page, we see velocity head in both formula. That means velocity head is an important element in both kinds of head loss calculations. Second, HF is proportional to pipe length L and inversely proportional to diameter D. That means a longer and a narrower pipe will have a larger major head loss. But for minor head loss, it is nothing to do with the length and the diameter, but it depends on the boundary shape varying locally. Third, we see two coefficients, lambda for HF and zeta for HJ. The following story will be mainly about lambda. To talk about flow region, we must watch the Reynolds experiment at first, with which we can understand the friction characteristics of different flow regions. Then we will learn how to distinguish these two regions. In the picture is an apparatus of Reynolds experiment, which was first used by Osborne Reynolds, a British engineer and physicist. There are some locations marked A, B, C, D, E in the picture. A denotes the experimental pipe ridge that is uniform and straight, so in it the flow is a uniform flow. The valve at B can control the discharge rate and consequently can control the velocity in the tube. C is the free surface of the indicating liquid in small cup. D is the free surface of the flow upstream. It's steady owing to the overflow outlet on the left. E is the exit of the colored liquid to the experiment ridge. On the experimental ridge, there are two piezometric tubes, number 1 and number 2. We note there's a level difference HF between the liquid top in the two tubes. In the time of the experiment, we measured flow rate Q in advance. Then we watched the change of color liquid along the flow and the record value of HF. This is what we can see in the experiment. As the velocity increased, the color line varied from a constant line to fluctuating line and then unstable line. At last it appears and all liquid in the tube is dyed blue. The color has been mixed up completely. The regular flow state is called the laminar flow region, while the chaotic state is called the turbulent flow region. In between is transition flow. These are two photos to show performance of different flow regions in reality. We see laminar is regular and turbulent is mixing by eddies. Please understand the equations here according to the picture, especially the relationships of flow elements in a steady, uniform flow. We can see at last that the measured piezometric had decreased, or in other words, the lost potential energy was given to friction work, namely the frictional head loss, while the kinetic energy isn't changed. This is absolutely a good way to study the major head loss, HF. At mean time in experiment, the mean velocity can be obtained by a cup and a stopwatch for the discharge with a given pipe diameter. Now the results are shown as in the diagram. We should note the axis title are both in logarithm. Why? It's because the experiment velocity can be from very small to very large, sometimes different by several orders of magnitude. We can use logarithmic operation to shorten the data distance. After logarithmic operations, now the data points scatter like this. We can find 3 stages with velocity change. Number 1. While the velocities are small, data points fall on a line with a slope of 45 degrees, which means HF depends on mean velocity linearly. This stage corresponds to regular flow performance and is what we call laminar flow. Number 2. As the velocities get bigger, data points begin to scatter and form a dot zone. In this zone, when velocity increases, the points locate on lower route like the red curve shows. But when velocity decreases, the points locate on upper route like the blue curve shows. The flow in this zone is called transition flow between laminar and turbulent. Actually, the range of velocities in this zone is so narrow that we usually don't talk much about it. Number 3. While the velocities are large, data points fall on a line again, but with a slope of 60 degrees or so, which means HF depends on mean velocity exponentially, with the exponent value between 1.75 to 2.0. The flow up to this stage looks chaotic and is called turbulent flow. Here's a table to classify the characteristics of different flow regions. However, by far, the criterion of flow region has not been referred yet. It will be talked about in next part. It is part 2.